In this video, we're going to talk about intake, indexers, and flywheels. Like how all claws are usually put on the end of some kind of lift mechanism, usually the intake, indexer, and flywheel are always working together, though there are instances where a team might use only an indexer to accomplish a certain task in the game. But alright, let's look at this example. This is example where we have an intake, Dexer, and double flywheel, one of two types, I guess you could say 4 types of flywheels that we use in VEX, and yeah, I'm gonna go through it. So in the year this is part of a robot. In the year this design was used, they had to control these tiny yellow balls, and how they did that was they built some kind of intake structure. As we see here, there are 2 sprockets, and in between those sprockets are a number of spacers. In my opinion, they could have done this more efficiently by just, instead of using all these spacers, put in maybe 2 shaft collars. And why 2 instead of just simply 1 is that between these 2 sprockets, rubber bands were running across. And so this does create a tension force that naturally wants to pull the 2 sprockets together. But I've found in my experience that if you just got rid of all these spacers and just put 2 shaft collars are, we have one in this file, pieces like this, right, with the set screw that digs into the axle. If you have 2 shaft collars on either side, the sprockets will not come together, okay? And so let's think about this. The intake in some kind of ball control mechanism is the part of the robot that brings the game piece into the robot, right? So imagine we have a ball around where my mouse is, and then you drive into it using the drive base, and then you use the intake that is spinning counterclockwise to pull in the ball, right? And the ball has to usually travel somewhere. So in some robots, that'll mean it just comes straight into the robot. In this case, in this robot, we have this back ramp here, right? So the ball goes up against the back ramp and goes up into this area of the robot, okay? And then now we've moved on to the indexer section of the robot. The indexer section usually is run with some kind of chain, usually chain with tank thread, so that, well, yeah, with conveyor belt links so that you can put in these flaps onto them, and this allows you to push the game piece along in the robot, because usually you don't just have an intake that feeds directly into an indexer, because let's say you're driving around the robot, right? And this year, for this game, for this robot, they had to pick up a bunch of yellow balls. You picked up the yellow ball in one location in the field, okay? But you don't want to fire it immediately necessarily. You want to position your robot in a more advantageous position before you shoot the ball. So you can store balls usually in your indexer system and control when balls are brought from, well, the beginning of your indexer, which is basically the location it shares with the intake, to the end of the indexer, where it shares its location with the flywheel. Something you want to know about the indexer is that you have to account for making sure that the ball, assuming it's a ball, though it could be, like for the game that we're doing this year as I'm making this video, we have these foam discs, so it's not always a ball, but you have to always make sure that the indexer is accounting for like the transition from the intake to the indexer and the transition from the indexer to the flywheel. And what I mean by that is that something should always be in contact with the game element. If something is not always in contact with the game element, you're just going to have a gap in your system, which will either be solved by getting another game element to push the game element stuck in a certain position, but that's just inefficient, or your mechanism's just not going to work at all because you have a dead zone. So you have to check for this in CAD by, well, frankly, manipulating the game element around your intake and then seeing how it transitions into your indexer, and also doing the same thing from the transition from the indexer to the flywheel. Okay? Yes. So some gear ratios. I mean, for an intake, you're bringing the game element into the robot, and the indexer is moving the game element along the robot and also acting like it's a storage compartment. But both of these mechanisms are doing something similar. They're moving the game element around, right? So the gear ratios you usually use for these mechanisms are like 3-to-1 gear ratio off of a green motor cartridge. That usually works. For this design, that always works. For this design, I believe they use simply looking at this. No, they did not have the chain. Usually chain would be wrapped around these two, but they used a 1-to-1 gear ratio because there's no gearing, right, and just feeds directly into this green motor gear cartridge, and I assume they used the right cartridge in the design, but maybe they didn't. Okay. And I mean, like I've said in other videos, this is also a kind of thing that you need to experiment with. You need to see what works. You want to optimize your mechanism by making sure you have enough torque, not only for the mechanism to actually work, but also so that the motor doesn't easily overheat. Okay. But considering that parameter, you want it to be as fast as possible so you maximize the efficiency of your robot. So something you have to try out. I guess 1-to-1, I can think of a few examples, has worked. So for intakes and indexers, I'd say the typical gear ratios are like 3-to-1 or 1-to-1. Okay. Now we're going to move on to flywheels, and these are a bit more complicated. Okay. So how does a flywheel work? Well, first we usually have some kind of indexer system that brings a game element to the flywheel. And we have many different types of flywheels, but I'll just first explain how this particular one works. Okay? Or in kind of general terms. Flywheel involves spinning a wheel at a super high speed so that when a game element makes contact with it, it shoots the game element out, usually like as a projectile, so that it flies in the air, okay, and goes towards something, and usually travels in some kind of an arc. All right, and these kinds of mechanisms usually do not use that much torque and rely on getting up to a very high speed first before interacting with the game element, because from that point, how it works is, well, you have to try to reduce friction as much as possible in these systems because they're running at high speed. But once they make contact with the game element, they lose some speed while making contact, but they're still starting at such a high speed that they're able to propel the game element forward. Now, this logic doesn't work for like a intake indexer kind of system. Like you're not trying to shoot a projectile, and usually the game element needs to be in contact with these mechanisms for a long time, especially for like an indexer, right? You need to be able to store a game element here and then start moving it from being static in place. Like it wasn't moving and now you have to start moving it. Okay, that usually requires some kind of torque. But for this flywheel, right, the ball has been moving. It's just being transitioned from the indexer once it makes contact with the flywheel, and then it's just now about speeding it up and making sure it flies very far. Now, you gotta be a bit realistic. You can't just use some crazy gear ratio like 1 to 1,000. That's not gonna work. In this case, they built a gearbox that was 1 to 25. Okay. Either side, because this is between these two gears, this being the driver gear and this being the driven gear. This is a 1 to 5 gear ratio. Okay, and then there's another stage of that, and so in total this is a 1 to 25 gear ratio. Now, I think this team realized that they wanted to get up to enough speed so that the ball would fly this far, right? So they use this 1 to 25 gear ratio, but they also might have realized that they couldn't drive this all off of one motor, and they needed to increase the torque of the system somehow. Now, if you increase the torque by just changing the gear ratio, it would decrease the speed, and that team probably didn't really want to do that. So what they did is they just slapped on another motor. That is something you can do in VEX Robotics when you need more torque, but you're not at all willing to sacrifice speed, and that's usually applicable to some mechanism like a flywheel. Then in that case, yeah, you might need to use more than one motor for your mechanism. Okay. Putting 2 motors in instead of 1 essentially doubles the torque of the mechanism without losing any speed. So that's an advantage. Now, how does this flywheel work specifically? This one is a double flywheel configured in like a horizontal fashion. Okay, imagine with me we have like a kind of table of horizontal, vertical style flywheels and double and single flywheel styles. Okay, and then so that gives us 4 different options. Though one of them I'm going to talk about, you'll realize just almost never is practical and makes sense. So, okay. The double flywheel, right? And this one's in a horizontal fashion. What does that mean? So, for this kind of flywheel, the trajectory of the game element can be varied, but it's harder to vary because it's horizontal, right? And okay, like think about it. You can change the speed of this motor, so you can change how fast these wheels are spinning, and that does give you some control over the trajectory of the game element. Like if you spin at a very high speed, right, you can imagine it's going to do something like this. So my mouse is moving across the screen. But if you spin at a super low speed, it's going to do something more like that. However, it's hard to like accurately control that trajectory. But yeah, and a double flywheel, I mean, there's 2 wheels here, so that's why it's a double flywheel. Okay. Then yeah, I'll move on to a single flywheel. And this is a single flywheel in a vertical fashion, right? And what does that mean? Well, so this horizontal fashion, we have like this kind of flat piece. And so it's almost like as if the game element is fed into the flywheel system, okay, when the wheels are flatter to like more parallel to the ground. Okay, though it is at an angle, so you can get some kind of trajectory. You wouldn't want to fire a projectile straight forward. You want to fire it up at, yeah, around a 45-degree angle is usually good, as you can see in this CAD. Now, for this mechanism, yes, it looks very bare bones, but I did it quite quickly. You have your game element being fed straight from underneath the flywheel. Okay, and this gives us some different options. So this one's first a single flywheel because there's only 1 wheel present. Okay, and it does similar things. It spins at a very high speed. You can even use 2 motors by having 1 motor on the left side, another motor on the right side, both driving the same axle that turns this flywheel. Okay, just something to clarify. But anyways, this wheel spins very fast. Okay, and when it makes contact with the game element, it shoots it out at this arc or trajectory, right? But something that's arguably better about a single flywheel is that when you vary the speed of it, okay, you have a bit more control of the trajectory of the game element. You're able to better control how far, like, you're able to better control different trajectories of the game element, because when you fire the projectile, okay, you always create some kind of spin with a single flywheel, because the game element is having to roll off the back wall of a single flywheel. Okay, and this is a vertical single flywheel, while it's just making contact with this wheel. And in this case, in a double flywheel, if you spin both of these wheels at the same speed to maximize the trajectory, you're not creating any ball spin. And why ball spin is important is that it usually increases the accuracy of shots. Just something that you can go try this out. Grab a basketball, try tossing it to your friend without any spin. I mean, I'm sure you'll be able to do it, but then maybe take a step backwards and do it from a farther distance, and try doing it with a spin and seeing which shot's more accurate. It's just a natural physics phenomenon. When you have spin on your shot, it is usually more accurate. Now, a way you can get around this with the double flywheel is decreasing the speed of one of the wheels relative to the other, so then you can create some kind of spin, okay, because there's a difference in speed. But then you're not taking maximum advantage of the power of these two motors, right? In this single flywheel, let's again assume you had two motors. They're both driving the axle, but from different sides, right? You can spin this at full speed, right? But you're still going to create that backspin because it's going up against this back wall here. Okay. So now we filled two. Now we've explored two of the different 4 options in our chart. Okay. Now I'll briefly talk about a double flywheel that works in a vertical fashion, but we don't do this in VEX. Sometimes we might do it in FRC if you're ever interested in doing that competition in the future. But in a double flywheel that works more in this kind of vertical fashion where the game element is feed from directly underneath the flywheel, sometimes an additional second wheel that's usually smaller in diameter than the main wheel is put around where my mouse is at the very end of the hood. Okay, and why do you have it there? So you can create even more spin. Usually this wheel is spinning in the opposite direction, and that allows you to create an even greater spin as your game element exits exits the flywheel. Okay, so now that's 3 out of 4, but that variation we almost never use because the advantages of getting that kind of spin, right? You have to sacrifice a whole motor for that, and usually it's not worth it in VEX because we only have 8 motors, while in a different competition like FRC, we have over 16 motors. So yeah. Right. Okay. And so that leaves one more variation where you take a single flywheel, but you shoot it in this more kind of horizontal fashion. I'm just going to manipulate the file here. And we're just going to do this. Okay. And then all of you over here. All right, and let's ignore this bent part to the right of the green line. Okay, so more horizontal flywheel like this. Usually you'd angle this at 45-degree angle. That's like the optimal angle for shooting. Okay, and you have your game element traveling up here. Okay, and you just have a single wheel spinning. And instead of having the second wheel here to create more spin, you just have your game element rolling off this back wall here and going straight forward for a shot. Okay. And I mean, it kind of works similar as this design, just that simply you replace one of the wheels with another, with a wall. Okay, so I've already covered some of this, but I'll try to put it more concisely what the different advantages, disadvantages of each of the options are. First, we're going to completely ignore the double flywheel vertical option that I talked about a bit. But okay, why would you ever choose trying to shoot your game element horizontally like this when yeah, why would you ever do that? Well, in this other option here, right, where you shoot the game element more vertically, or like the game element comes up into the flywheel from below it, right, this mechanism naturally takes up more space. And sometimes you can afford to give that kind of space in a robot, but that's not always the case. Shooting your game element at this more like horizontal setup is usually more compact because it can feed from an indexer that is feeding game elements at it going at a 45-degree angle instead of having to travel straight up your robot when you usually have a starting height restriction of 18 inches, right? Diagonal line is longer. The diagonal line across this cube is longer than the horizontal line of it. Okay. Now, but why would you ever use what advantages does this vertical flywheel system give? Because it's set up like this and you have a black wall here and you have a flywheel angle at this position, right? Depending on how fast you spin this flywheel, you'll have greater control over different trajectories of your game element. So if you get really good with a sensor, if your programmer is able to detect how far you are away from the target, right, and you do some physics calculations, or maybe you just do a bit of guess and check to just see what works, you could set it up so that this flywheel spins at different speeds depending on how far you are away from your target, and you can theoretically make almost any shot accurately. For this one, it's a lot harder because varying the speeds will vary the trajectory, but because you're not rolling off of a backboard that's curving this way, it's just not going to work as well. Okay. Now, comparison of why would you ever use this double flywheel over this single flywheel with beam here. So if we think about spacing in this orientation, right, it's just looking at this, right, it was pretty easy for this designer. Okay, not that it's easy, but this designer was able to set up this mechanism to have two motors when there were two wheels involved with shooting the projectile, right? And you can look at how clunky this gearbox is. Now, imagine if they had to copy basically everything to the bottom left of this C channel and put it around where my mouse is drawing a rectangle, right? They have to copy this whole gearbox, flip it 180 degrees, and slap another motor over here. That would be outside of sizing restriction, right? And that means it's very hard to make one motor power one flywheel when it's in this specific orientation, right? It's not impossible, but it's harder to do. So that's why some teams will just simply go with two flywheels, because at least they can use two motors for their flywheel instead of being restricted to using only one. Now, if I go back to this example just for a moment, right, because the orientation of this is a bit easier to deal with, in my opinion, so you're able to create two separate gearboxes, each with a motor feeding into this final axle that the flywheel is on to drive it. Okay, it's a bit, yeah, it's a bit confusing. Honestly, during the season, we're probably going to hopefully get through multiple robot iterations. So I would just pick one of them. You can talk to the mentors or your team about it and figure out and just go with it and just try it out. And maybe it'll work out, maybe it won't, maybe it's the best solution, maybe it isn't. Robotics is about trying things out. Okay, but we have these technically 4, but in practice, 3 different flywheel options. Okay, and then you always usually have, okay, so not always, you usually have some kind of intake or an indexer system feeding your game element into your flywheel system to shoot it out.